Stanford University, Alfred Suppes, who will speak on invariance and meaning.
Well, thanks very much, John. There are many stories I could begin with about Tarski. I knew him for many years, and I didn't quite know him as a student. I was already a faculty member when I met him. I was a faculty member, a very junior faculty member at Stanford. But he had a lot of impact on my intellectual life, and I can remember many things to say about him. I certainly remember the kind of thing that John has mentioned. And he always had lots of ideas about projects. Those of you who were younger than Tarski like me, and almost everybody here is in that category, can remember how those projects went. Alfred was very good at thinking up something, and he counted on the rest of us doing the work. But that didn't mean he let control go. He also wanted to monitor carefully and had lots of remarks and lots of ideas about how things were to be organized, and lots of detailed conceptions of exactly how one should think about matters. And so he was an active collaborator and more than played his role. He got me into a lot of different things. One of the things was the organization. He had the idea, along with Bet, to reorganize and reactivate the international group in logic, methodology, and philosophy of science, which got disrupted by World War II. And Alfred really was the major force in organizing that again. And we held at Stanford in 1960 the first of the modern congresses. And he again was the inspiration and the driving senior force. It was my job to find some money from the National Science Foundation and get it organized. But he really was the moving spirit. And that was the way it was. I knew Alfred until the end of his life, and when the phone would ring and it was Alfred, Alfred would always say, well, he'd want to know how things were going and all, and then said, well, I've been thinking, or I heard about the following, and he'd have some idea of something that should be undertaken. Maybe it was someone from Poland who needed to give a lecture, or maybe it was another conference one ought to think about, but he was always full of such ideas and very active in his in wanting to realize his conception of how the intellectual life should be organized. I think there's another aspect, though, of his intellectual work I would want to mention, and that is also had a very strong aesthetic sense, had a very definite idea about how things should be written, how they should be expressed, and also about how many other things outside of papers should be handled. And very proud of his garden, and generally very aesthetic in his considerations, and played an important part in his intellectual work and in other aspects of his life. I could say more, but I did want to say that, and maybe I'll think of a couple of other particular remarks the second lecture. Now, what I want to talk about today, invariance, is something that I've written about myself, other people here have, and it's a big and complicated subject. And so what I want to mention are certain, begin with some common remarks, general remarks, and some examples. And then I want to spend the last part of the lecture, a fair part, on an important example from examples from ergodic theory. Of removed a bit from logic, but not entirely, but I think of a very considerable philosophical importance and a philosophical interest. And I'll try to explain that as we go along. So the lecture will be broken into these two parts. I want to begin with some general considerations that I won't go into with as much care. So, whoops. They're always a little bit finicky. So let's just begin with some common meaning of invariance. Look it up in the dictionary, for example. Unalterable, unchanging, constant. But then the question is, what is unalterable or unchanging? What are we talking about? Well, ordinarily, we talk about being invariant a property of an object or a collection of objects or of some phenomena. Examples. Well, a very familiar example, the shape of a cup. Child learns early is not changed by rotating it. The contents of a glass don't stay invariantly in the glass as you tip it back and forth, but the shape of the cup is invariant under standard Euclidean motions. The speed of light in a vacuum. So this notion of unalterable or constant is the key idea. And let me begin with a well-known theorem of Tarski's. And I'll give you two formulations. This is in the Tarski led to the publication, first given in talks by Lindenbaum and Tarski in 32 and 33. And this is about the well-known result about that what is invariant under 1-1 mappings of the world or the domain or the universe, as we would say, onto itself, and that is just logical properties. And this is the formulation given then. So the way he puts it here, every relation which can be expressed by purely logical means is invariant with respect to 1-1 mappings of the world. And this is the most general kind of result. And a way I think of this, in a sense it'll be clearer later, as the most general kind of result of you might have. Now, in the last book of Alfred's, the book on set theory without variables with Jevant, then the same thing is stated, but in a somewhat different way. I thought it was interesting, 87, more than 50 years later, he returned to reformulate these ideas in a very nice way. He defines at the top a logical object is invariant under every permutation of U. And when he says derivative universe, they mean here where you have relations, etc. So then they show a theorem on the basis of this. One can show, for example, that for every non-empty universe, there are only 4 logical binary relations between elements of U. And these are the familiar 4. Universal relation, empty relation, identity relation, and diversity. In other words, you're not going to express much that is invariant in this very wide fashion. Now, some of you might think that this was the main way that Alfred thought about invariance in terms of simply of logic. But in fact, those of you who are familiar with the Banach-Tarski paradox will know that major theoretic matters and invariance are important there. And in Alfred's book on cardinal algebras, there's quite an extensive treatment because invariance under measure is an important topic there. I won't go into that in this lecture, but I just mentioned his own interests extended into several areas in important ways where invariant matters are of importance. Now let me give some simple examples. Here's a good example. This is from a drawing of a Palladio villa taken from Palladio's book on 4 books of architecture, one of the most famous books in architecture. And the bilateral symmetry we can see both in the elevation and in the plan, a passion of his. Bilateral symmetry is important in all kinds of things. One speculation is because of the approximate bilateral symmetry of all of us. Here's an example from a Chinese vase, a similar sort of thing. And here is another example, which I like even better, Chinese, of bilateral symmetry. Very elaborate, but still satisfying very closely bilateral symmetry. Now, what's that got to do with invariance? Well, as I'm going to say in a moment, one of the important aspects of invariance is symmetry. But before I come to that, here's a case of rotational invariance. Not under any angle, but under 90 degrees. And again, taken from a Chinese This is from that famous publication of Jones in the 19th century on the grammar of Chinese ornaments. Many beautiful examples. I just picked a couple. So when we talk about invariance and symmetry, there's lots of visual things to be said. So an essential aspect of invariance, and closely linked in all kinds of discussions, symmetry, and I'm only going to mention this briefly because that's not my main concern today, but it'd be very easy to give the talk entirely around that. So the general geometric viewpoint is derived from Klein. For a given group of transformations of a space, find its invariant properties, quantities, or relations. Tarski's theorem when you don't put any kind of structure on that space. These transformations we also call, and are the group of automorphisms of a space, define the geometry, the automorphisms of the structure, carrying the structure into itself. Now, within that geometric framework of invariance, then we have the standard geometrical characterization of symmetry. A figure is symmetric under the group if every automorphism of the group maps the figure into itself. So in the case of bilateral symmetry, the mappings are mirror images in the plane, which I say here. Figure symmetric under various rotations, that's the last example, and of course the circle above all invariant under every rotation. Familiar examples of invariance, now moving a little more generally, the notion of betweenness. That's a familiar, I don't know how many of you know, a very nice papers written by Alfred and I forget his collaborator at the moment, on affine geometry. But they use only the notion of betweenness as the primitive for affine geometry. That only has one problem. It's a beautifully simple primitive, but the axioms use lots of variables and are rather complicated. For Euclidean geometry, again an article of Alfred's, betweenness and congruence. Now another very closely related concept of invariance is meaning. Familiar examples. Orientation, such as Aristotle's up and down. Remember, in Aristotle's world, we had a clear down toward the center of the earth. And that was also the center of the universe. Is not meaningful in Euclidean geometry. In fact, it's sometimes been speculated why were the Euclidean geometers so clever as to not try to satisfy up and down. Well, so orientation's not invariant under the Euclidean group of motions. It is meaningful, on the other hand, to take a different notion, to compare the lengths of two line segments, regardless of whether they are parallel or not. So we talk about meaningfulness in relation to invariance. And those are simple examples. So in other words, in the case of orientation, we take another Euclidean motion, we change the orientation. Congruence is something different. Now, there are many stories and many details and distinctions to be made. For example, in affine geometry, it's not meaningful to compare the length of segments unless they're parallel, including lying on the same line. Otherwise, because you can change, if you have a affine geometry like this, here's one axis, here's another, you can stretch them in a differential way. Stretch this more than that, and that just, if you have one segment here and one here, that immediately disturbs as unconstant the congruence. In projective geometry, on the other hand, the concept of betweenness for points on a line is not preserved under projections from one line to another. In the case of projective geometry, we need the four-place relation of separation. Here's an example. See, on the first line without the primes, C is between A and B. On the projection from P, C prime is out, A prime is between A and C. On the other hand, separation is preserved. The pair AB separates C and D. And correspondingly, the pair A prime B prime separates C prime D prime, and conversely for CD and C prime D prime for A and B, and A prime B prime. So you have that nice, beautiful notion of separation. So the notion of order even, something we sometimes think of as very fixed, very much depends upon the geometry. Now, another somewhat stricter notion is sometimes to say there is a strong notion of objectivity about invariance. So you sometimes see a discussion under the title Invariance and Objectivity. And this kind of analysis, let me give 3 physics examples. In classical physics, distances and times between point events are invariant for observers moving relative to each other and with constant velocity. And what you can show from that is that 2 inertial observers are related by a Galilean transformation, and the standard group in classical physics is the group of Galilean motions, or Galilean transformations. Now, notice that the notion of objective here is philosophically quite strict, because the measurement of the direction vector between these 2 events is objective in the sense that all observers at rest with respect to that given observer would agree about it. But it's not invariant for other observers moving relative to the first one. And so the strict meaning is objectivity required must be invariant for all observers that are invariant. That are inertial observers, moving with constant velocity with respect to each other. So if you want to talk about a meaningful notion in classical physics, the argument can be made that you must consider notions that have this kind of invariance. And that's a familiar argument. Now, the second example is also classical physics, but rather different, not quite as familiar, and that is Emmy Noether's theorem, dating from 1918, which I'm putting in just an informal way. So if you put it verbally in a somewhat technical way, to every one parameter group of diffeomorphisms, this is about Lagrangian mechanics, is formulated here, of the configuration manifold of a Lagrangian mechanical system, which preserves, and that's important, the Lagrangian function. Then there corresponds an invariant quantity, which is a first integral of the equations of motion. And example, the first is if you have translation of the system, of the mechanical system, in a given direction, preserves the Lagrangian function, then the center of mass moves in this direction with constant, that is, invariant velocity. A second example, very closely related and important, of that same phenomenon, of Noether's theorem, and the examples are what are interesting here. A system admits rotations around a given line. That's given. Then the angular momentum with respect to this line as axis is invariant. That is, the angular momentum is constant in time, and as we would put often in physics, and it's often Noether's theorem is paraphrased not just in terms of invariance, but conservation. So what this says, then, you have conservation of angular momentum because it's constant in time. So this is a standard application in physics of invariance. Now, a third example in special relativity, invariance for 2 observers of the proper time of a moving particle is sufficient to derive that their observations are related by Lorentz transformation. So you can use, in other words, now qualitatively or axiomatically, invariance of the proper time. Now, the proper time I've defined below. This is the proper time interval of 2 points lying on the trajectory of a particle, not space-like. Tau 1, 2 for the 2 particles, the 2 events, 1 and 2, 2 points. And it's this T1 minus T2 minus 1 over c squared now, and then the square of the sum of the squares of the coordinates. Notice, of course, this is quite different now. What is important here as a qualitative observation, and is the fundamental difference between classical physics invariance and special relativity. There you have a separate invariance of time and space. We have two separate things in the classical case. Invariance of distance, that's spatial distance, and invariance of temporal distance for different observers. Here you have this mixing of time and space. Notice, of course, from a geometrical standpoint, both the classical case and the special relativity are special cases of affine geometry. It's a flat geometry. We don't have any general relativity here. We don't have any disturbance of the affine character of the geometry. And yet the character, so that they're both these are then subgroups of the general affine group, but of great physical importance. One, a very good approximation for much ordinary phenomena, and then secondly, the very important case for special relativity, fast-moving particles, etc. So in this case, we can start with invariance as a way of deriving the Lorentz transformations. You can prove, and as a matter of fact, John mentioned the old axiomatic method symposium. Leon sitting over here. That was in fact the paper I gave proving that at that conference. So a way of summarizing about proper time is proper time has objective meaning independent of the observer. And that's a familiar observation in special relativity. Also proper time, and this is not as often noted, is a complete invariant. That means that invariant itself is sufficient to derive the group of Lorentz transformations. You don't need other kinds of assumptions. For example, you don't need to bring in, you have a constant c, you don't have to bring in directly the velocity of light being constant. All right. So now another area that I've completely omitted here is talk about invariance in statistics. And there's a big controversy about that. Ernie Adams sitting here reminds me of it. And disputes, for example, particularly in psychology, about, for example, tests. So if we have a test that we claim only has really ordinal properties, but we in some way scale that, and now we take the mean of the class or the mean of the students in the school, is that a meaningful measure of anything? Now, I'm not going to enter into that here. I just want to say that that's a very good example where invariance, the temperature rises as the discussion proceeds. David Blackwell probably never... David, where are you? I saw you. Raise your hand, Daddy. I don't know that David ever made any comments on this particular matter, but he's more than aware of it, I'm sure. It's a lot of people have written about it. I'm not going to say anything more here today about that. I want to turn to this, but I just want to, because I have been involved in discussions of that in relation to measurement. That's a very appropriate topic that in this survey is not being given its due. Now I want to turn, this has been rather quick, and I want to turn now to a detailed case because it interests me, it's forced me to learn something about ergodic theory. Certainly don't ask me any questions that a specialist should answer. But I know enough to discuss these examples because they have great philosophical interest for me, and you'll see as I get into them why. But in addition, the discussion I want to give makes three very important uses of invariance. First is the use of invariance in defining what we mean by ergodic, and we'll come to that. Second, the very surprising fact that entropy is a complete invariant for the measure theoretic isomorphisms of familiar stochastic processes. The measure theoretic isomorphism is for something very complicated. And here you have a single real number that gives you immediate information as to whether two processes have a major theoretic isomorphism, which means they have the same uncertainty structure. You can map, you have a mapping that carries one from the other, preserving the probability of events. That is, an event is mapped to a new event, and the new event and the mapping has the same probability. I'll say that more precisely later. But that's very, very surprising. And the third is the invariance regarding, that I want to end with, regarding determinism and indeterminism, or determinism and deterministic processes mechanically, and stochastic. So I have a lot of axes to grind here at the end, philosophically, if I get there. But in the meantime, two very pretty applications of invariant notions. Now first, a one-liner here for a probability space, just a set omega, a sigma algebra of sets that are events and a probability measure. And what is important here now for I'll give just some elementary distinctions. T is a transformation carrying omega into itself. But T will have a special quality. We have in mind here stochastic processes. We'll make these discrete, so they go along in time, one step at a time. And T will be a left shift for our discussion. I'll say what that is in a moment. But these are properties that T must have. Above all, T is measure preserving. Notice P, T inverse A equal to P of A, that is the probability. We will make T 1, 1. So we could write P of T of A is equal to the probability of A for all the discussion here. So that it directly preserves in that fashion. I won't go through these other conditions. You can expect them. The measure preserving one is what is important intuitively. That's the particular and a necessary one to think about. Now, a left shift. So T has this kind of property. It could be a right shift. We'll use a left shift. So X and Y are sample paths. So we have X1 is what happened in that sample path on trial 1. X2, what happened on trial 2. Y correspondingly is the sample path. Now, T is a left shift, meaning that if X is X0, etc., then T for Yn minus 1 equals, if it's a left shift, then if Yn minus 1 equals Xn, T of X is equal to Y. And that goes for all n. So you can see how I've written it there. Okay. Now the important notion about left shift. Two important notions. A is invariant under T if and only if T of A equals A. Remember, we're making it invertible. Secondly, A is non-trivial if and only if its probability is strictly between 0 and 1. Now we can say, give the definition of T being a transformation that's ergodic for the given space in which it lives. T is ergodic if and only if there are no non-trivial invariant sets. Now, that's fairly high-flying there in definitions and the like. Let me take the simplest example. So we're given a space and a shift T, and chi is a stochastic process on this space. Chi is ergodic if T is. But now, here's the simplest example of a non-ergodic process. So you give a feeling for non-ergodic. The trivial Markov process, heads goes to heads with probability 1, tails goes to tails with probability 1. So what happens? The sequence, we'll make the initial probability of heads and the initial probability of tails equal to half. Then the sequence of all heads, so each omega I or X in omega, T carries A into A, obviously, because it can't go elsewhere. But the probability of A is a half. So this process is not ergodic. Now, there's a better intuitive way of explaining about a Markov process that's equivalent. So for Markov processes, I can say something really simple. When is a Markov chain, and let's deal with discrete trials and finite states here. Think of that just like this in a very simple way. And these ideas generalize. But in that very simple to say when the process is ergodic. If and only if there is a unique asymptotic distribution of the probabilities independent of how the process started. That is, what the initial probability distribution of having heads or tails might have been. And you see in this process, clearly that's not going to be the case. Depends very much on how you start. If I start with heads probability 1, then everything remains heads. Okay? So we have a very natural characterization of we have a fairly, we need a general machinery here, but we have a very straightforward definition for Markov chains. So keep that in mind. Now the next notion we want to introduce is entropy. A familiar notion, and we'll just review it here. So we just have, we're just worrying about heads and tails. We're just one trial. Then the entropy, say the probability of heads is P1 or P, and the probability of tails is 1 minus P or P2. Then the entropy the entropy H of this one trial phenomena is just minus the summation P sub I log P sub I. The very familiar formula. For a process that is a stochastic process, the entropy H is the limit if the limit exists. I didn't put that on it, but if the limit exists, it's the limit of 1 over n H of x1 to xn. For a Bernoulli process, now what is a Bernoulli process? Because that's a very important example for the developments here. A Bernoulli process is a zero-order Markov chain. That is, what happens on trial n is completely independent of what happened before on n minus 1. And it's the same probabilities on every trial. For a Bernoulli process, the entropy has a very simple form. It's just like up at the top. Minus summation P sub I log P sub I. And because the entropy on every trial is the same, and we have, and I won't give the proof, but it reduces to n hx1 divided by n. For a Markov chain, the entropy is nearly as simple. First, we sum inside, like sum over I, Pij log Pij. So for a given I, we're just summing across the row. And then we take the sum of the rows. Okay? We're not going to use this deeply, but it's important to have it in front of us. One thing you see, what's very important is it's a very simple expression. Now, types of ergodic processes. Well, first we have ones with zero entropy. That is, everything's predictable. There is the, I hope, the simplest example of an ergodic process with zero entropy. So we have heads and tails, but we're mixing all the time. Heads, tails, heads, tails, heads, tails. Transition is shown. We start, say, at probability H1 equals 1, but the distribution will clearly be asymptotically 1/2 heads, 1/2 tails, independent of how we start. Secondly, we have positive entropy, more important case. Not all measurements predictable, but some may be. And we have here the important notion of a factor. We can have a factor of a process, which is a restriction of the process to a sub-sigma algebra of events. So I could easily put a matrix up here that a piece of it could be predictable, but other parts aren't. And we have the important notion of K processes, K for Kolmogorov. A K process is one in which no factor has zero entropy. In other words, no factor, no subpart has predictable behavior. Example will be Sinai billiards. I'll talk about briefly in a moment. And a familiar example, Bernoulli processes. we've just been talking about. Intuitively, without trying to be too fussy about it, flipping a coin half-half is one of the most random things we can possibly imagine, and used in all kinds of discussions exactly for that reason. There's no history, there's no past, there's no future in the sense of that everything goes along always the same and always with the same chances. Now, a familiar and property of ergodic processes, it's often said, well, what is an important feature of an ergodic process physically? An important statement is that the time averages equal the space averages. Now, what does that mean? That means if we take some event and we study its behavior, then we should be able to get all we want out of looking at the spatial ensemble of the process, or everything we want to know about the process can be learned, except for sets of measure zero, about a sample path of a single particle. That's what's characteristic of ergodic. So every sample path, except for those in a set of measure zero, exemplify the entire characteristic features of the process. And that's what's called the fundamental theorem, ergodic theorem. And what this IA is just take an event A in the space, in the original probability space. I of A is just the characteristic function of A, and omega is some sample path. Then as we take repeated iterates of T, then the relative frequency of the appearance here, notice we're dividing by the number of trials, will just equal exactly the relative frequency will have as a limit the probability of A. So the sample path repeats all exactly the features of A as omega wanders in and out of A. And this will be true for every measurable event A. Now that's a remarkable kind of mixing, and that's exactly what's characteristic of an ergodic process. So now we want to go to the next notion. So all we really have here in this definition of a shift, you might not have noted before, when it's ergodic, we have only trivial sets are invariant. And now we had the notion of entropy, and now we want the notion of isomorphism of two stationary stochastic processes. Well, I even wrote down, well, I left the definition of stationary. Two processes are stationary. I mean, a process, a stochastic process, is stationary when any n-fold multivariate distribution is the same if you shift it all to the left or the right in time. So it's invariant. The multivariate distributions, in other words, the finite multivariate distributions are invariant as to time. Then the process is stationary. Take the familiar case of heads and tails. The probability of two heads in a row is exactly the same whatever pair of trials you take. 15 and 16, 1 million and 1 million and 1. A stationary process like that, you have exactly the same probability. So stationary is a very intuitive notion, and of course doesn't hold from minus infinity to infinity, as we like to say mathematically, but holds for large patches of experience as an approximation. So the definition of isomorphism is just for stationary processes. And the meaning is that we can map the probability structure of one into the other. I had some material on there on applications I'm not discussing here. Now, Let me just say, I'm trying to not put all of this to give you too much stuff here, to give you the technical definition of isomorphism. Well, I'll just say it quickly. So we have two probability spaces, and we have two shifts, t and t prime, and then we have a function phi, and we take sets of measure 1 in each for technical reasons, phi matching omega 0 into omega 0 prime. And what are the characteristics of this isomorphism function? As you'd expect, it has to be 1-to-1 onto, from psi 0 onto psi 0 prime. And important here, P of A maps into P prime of A prime, its image. And we have this relation between phi and the shifts. Phi of T omega is equal to T prime phi omega. Those are the main properties. What is important, though, intuitively, is you're claiming rightly that you have the same uncertainty structure in these two processes, because you have this mapping that preserves a 1-1 mapping preserving probability. Now, the question was originally, if you, by B1212 and B131313, we mean what? Two Bernoulli processes, one of which you have two outcomes, like heads and tails, and the other of which you have three, a third, a third, a third, as the probabilities. Now the question in, say, circa 19, as late as circa 1954, was, are these two processes isomorphic? They have a lot of similarity in their probability structure. They're, of course, different processes. But it was not a simple matter to settle it. And in fact, it was settled in roughly 1958 by Kolmogorov and Sinai, with the result that two Bernoulli or Markov processes, ergodic ones, are isomorphic, then their enthalpies are the same. But of course you can show immediately, you can see immediately by the contraposition, the enthalpies of P 1/2, 1/2 is not the same as P 1/3, 1/3, 1/3. And so they are not isomorphic. Then in 1970, a colleague at Stanford, Don Ornstein, proved the important converse, which showed that enthalpy is complete invariant. If two Bernoulli processes have the same enthalpy, they are isomorphic. And that's a remarkable example of invariance. That is, to be that all you need to know is the enthalpy to know that they're invariant. So you, on the surface, if you look at a Markov process and a Bernoulli process, remember, one has dependency from trial to trial, the other has independence from trial to trial. But if they have the same enthalpy, which is easy to construct, so they do, then they are, you know immediately, they are isomorphic. That going from one to the other was proved a little bit later. Just to summarize, if we want to state it explicitly about Markov processes, any two irreducible stationary finite state discrete Markov processes are isomorphic if and only if they have the same periodicity and the same enthalpy. And the corollary then, Markov processes can be isomorphic to Bernoulli processes of the same enthalpy. That was easy to show once the two results of Kolmogorov and Sinai and then by Ornstein were known. Okay, you might say, well, we could stop there, but there's more. And that is to ask, what is the force of the isomorphism? Now, it's easy immediately. Say I have a Bernoulli process and a strict Markov process that are isomorphic. It's extremely easy, if I have sample paths, to distinguish these two processes. They need to be isomorphic measure theoretically, but I can just run a chi-square test on the dependence. The dependence exists in the sample path of any one of the Markov process. What happened now affects what happens next. In the Bernoulli process, not at all. So they are clearly distinguishable. Now, can we impose another criterion, additional criterion, that brings them close together? So that's the next step. So the next step is to the concept of alpha congruence. And this imposes, nicely in terms of the earlier discussion of geometry, a geometric condition as well as a entropy condition. And let me give the kind of examples we want to think of here, so let me give them first before the definition, are physical examples. Now, it's old as can be, and a favorite example of philosophers in the 18th century, that a wonderful example of a mechanistic system is ideally a billiard ball moving periodically on a billiard table, with, of course, idealized no loss of energy, so it goes periodically. Now, it's another world, and a very complicated world, if you introduce a convex obstacle in the middle of the billiard table. And this is using a photon as an example, showing what the trajectory will look like in the first 15 or 20 steps with that convex obstacle there. And if you think of partitioning up this compact space, then it looks like that. These proofs work off the finite partitions. So now the question arose, and this is something Ornstein had, and his colleague Weiss had very interesting ideas about. Well, can we add something to the conditions to make the deterministic process and a stochastic version of it indistinguishable? Now, what prompted that in the first place? What prompted that in the first place was the prior extremely difficult proof by Sinai that, in fact, the purely mechanical motion of an idealized billiard ball, a photon you can think of if you want, that's better than a billiard ball, but think of a billiard ball if you want. The idealized motion of a billiard ball, no probability here, the idealized motion of the billiard ball actually generates an ergodic measure. Every point except the set of measures 0 is visited arbitrarily closely, arbitrarily many times, if the path goes on forever. So there was an inspiration here to do more than just the result on entropy. And they introduced the notion of alpha congruence. So this is the notion now. If we have two such flows, they're isomorphic, and we have a compact metric space in which the action is taking place, and they're alpha congruent if and only if for every omega, the distance between omega n and phi omega n is less than alpha, except for a set of points at m of measure less than alpha. So we have this alpha congruence. Now, what that is meant to do is to introduce in a very general way the notion of a variability or experimental error. So we think of points in M with distance less than alpha as indistinguishable due to inherent variability or experimental error. And so we have the following wonderful theorem of Ornstein's, the philosophically, in many ways, most interesting theorem I know of about mechanical systems, applicable to mechanical systems. There are processes, think of the Sinai billiard example, which can equally well be analyzed as deterministic systems of classical mechanics or as indeterministic Markov processes, no matter how many observations are made, if observations have only a bounded finite accuracy. So we have in mind, and here is then the realization of that. Pick an alpha greater than 0, depending on, for realism, however you think about the measurement accuracy. Define a biased coin stochastic process. Just two choices, heads and tails with a bias. Finitely partition the table. That's the partition I showed you. Ball will always be in one element of the finite partition. It stays in each element P of the partition for time T of P. So that time there can depend on the element. There are only a finite number of those elements. The ball then jumps to one of a pair of points according to a flip of the coin. The pair of points depends on P. Theorem, billiards, mechanically as we know it, and this S process of stochastic process of coin flipping are alpha congruent. We cannot distinguish with an unbounded number of observations, finite but unbounded number of observations, which model holds. They are both indistinguishable from each other within this important kind of framework. Now, notice, of course, if it only applied to billiard balls, we might say, well, so what? But it's exactly a kind of system we can get our hands on mathematically. What we want to say is that explicit theorems like this, for concrete cases, are extremely difficult. But they seem likely to be true in a wide variety of cases. That is, if we have an error of measurement, which we do have in all natural physical cases, then we are not going to distinguish nicely between stochastic and deterministic models of the behavior of the system. So transcendentalism is the outcome for determinism. It's not false to mirror Kant, to be philosophical now in the closing moments, to mirror Kant. Transcendentalism is the thing to say about determinism. If you think universal determinism is what governs the universe, then you can think that according to this line of thought, which is also compatible with various views about hidden variables, deterministic hidden variables in quantum mechanics, but you're not going to be able to prove it. So it'll be beyond what you can establish. And it seems to me that that transcendental view is what leads us to my final remarks about invariance, the one I was honing in on in all this discussion of ergodic theory. We can apply the same kind of argument about continuity. We can't have experiments that establish rigorously that phenomena are continuous. With any kind of randomness, variability assumed, we cannot distinguish between discreteness at a very fine scale and continuity. And so we get the observational equivalence of continuous on a given domain, models that are continuous and deterministic, deterministic and discrete, continuous and stochastic, stochastic and deterministic. And it's this invariance, the observations will support each of these four in the same way. So now I'm reversing it. The invariance goes from the invariant observations back to the differing conceptions. And what they suggest is that what we can know about the world is much more austere than our sort of folklore talk in physics. For example, about continuous quantities and about deterministic models. The final remark I want to make about that is that I think having an argument that establishes not the falsity of determinism, but its transcendental character, that is, you can hold to determinism, if you like, or indeterminism, but recognizing that either one can be supported to the same degree by the same evidence, is a way of getting rid of one of the worst bugaboos in the history of philosophy, the problem of determinism and free will and moral choice, or free choice. And so I wanted to end with that to say that we can bring a beautiful theory like ergodic theory to this final point about invariance. Thanks very much.
That is great to take one or two questions, if there are any questions or comments.
Your talk on Wednesday is independent.
Yes, yes. Completely independent.
Thompson?
You said that this might take care of the bugaboo of free will versus determinism, but one way of looking at it is that there isn't too much difference between determinism and physical indeterminism. That is, whether, for example, certain physical processes are completely deterministic or there's some absolute element of chance which follows certain other physical laws and can be exactly given. Still, there wouldn't be any free will either way, because these would be processes that wouldn't have anything to do with what a person was. It would be just all matter of physics anyway. So you still have no room for free will. In fact, I don't know that the notion of free will actually is conceptually coherent. So I don't see how this...
Well, I don't agree with that, and I'll say why briefly. But I want to emphasize that, of course, I didn't pretend to give here anything like a detailed theory of free will. To use a good old-fashioned phrase, the lecture is meant to be a prolegomena to a lecture on free will, not the lecture I'll give on Wednesday. But let me just say briefly why it bears. You see, the bugaboo in much philosophical discussion has been about universal determinism. And one of the ways of thinking about this that bears on what you said is, it isn't just a matter of free will. You might like some more austere formulation than free will. It bears upon the theory of computation. I mean, how do you give an account of computation in terms of devices that we build? We build them with intentions, and they realize those intentions most of the time beautifully in terms of computations. Correspondingly, any theory I would give of free will is much concerned with what I call, what the brain is doing lots of the time, natural computation. And so it's very important to begin with the theory of computation. And what is needed is to break the hold in our conception of the world by some austere view that it's either universally determinate or it's not. And that's all we can think about. And I think that's incorrect. But I can't give the more detailed argument now.
Question over here.
Your interpretation of Ornstein's theorem depends on the fact that these are just the structures we want to be talking about. There might be enriched structures for which an Ornstein-type theorem doesn't hold, where you could distinguish deterministic from non-deterministic processes.
Absolutely. But I don't think there are very many. I mean, that's a belief I would have. You see, I think the problem here, Saul, I mean, and it's an appropriate question, is it's a struggle to... it's a struggle to prove anything about real complex systems. Though there's lots of... Well, let me put it... you see, I don't want to try to... I'm not going to give you a knockdown argument. I'll give you some anecdotes. So... because I think it isn't possible to put together a knockdown argument. You have to give a kind of inductive argument. And again, I don't have the time here to lay out various cases we know a lot about, but there are many, many cases in chaos theory that are examples of how unpredictable the phenomena are and that fall within the framework we're talking about. And the anecdote I want to tell you is there was a wonderful article about 10 years ago in the Proceedings of the Royal Society by Sir James Lighthill, who was a distinguished applied mathematician and mathematical physicist who had wonderful ideas about classical physics, and particularly about turbulence and hydrodynamics and aerodynamics. And he said this article is an apologia because for 150 or 200 years we have taught students of classical mechanics with the hubris that, well, if they just worked hard the way we'd worked, most problems they encountered could be solved. And that is quite mistaken. In fact, the problems we give them and the problems we have solved represent, in my own phrase, an enormous amount of very careful cherry picking. That, in fact, almost no problems can we manage. It's only an occasional problem that can really be managed. And the kind of enormous calculations that have gone into various very simple chaotic examples. So, for example, if you don't believe this holds for the atmosphere in some form, look at the calculations that have taken place over this extremely adiabatic model, simple one-dimensional adiabatic model of the atmosphere due to Ed Lorenz, by the way, who was a colleague of mine in meteorology in Guam in World War II. That's why I know about it. So there are many examples like that. So I can't give you, in other words, a mathematical argument. I don't think that's possible. I think you have to work off of lots of cases.
You noted in passing that the last question was asked by the Patrick Suppes family professor of mathematics. Any other questions or comments? So if not, let's thank Pat again. Two announcements. One, you are all most cordially invited to join Professor Suppes now at the 11th Annual Alfred Tarski Reception, which will be held in the Mathematics Common Room on the western side of the 10th floor of Evans Hall, which for strangers is just really across the street from LeConte, a very tall building. Secondly, the second of the lectures this year will be given on Wednesday, same time, 4:10, but in an adjoining building, LeConte Hall, 1 LeConte. That talk will be independent of this talk. We encourage you all to come back for that. It's going to be on a physical model of the brain's computation of truth.